Part 2. Avogadro's constant is 6.02 times 10 power 23 mole. Determine the total number of ions that are present in 500 cubic centimeters of 2 molar calcium nitrate. Our first step will be determining the number of moles of calcium nitrate. Now, in case you're wondering why do we need to find the number of moles, then just remember that when it comes to Avogadro's constant, this refers to the number of particles present in 1 mole of a substance. Particles may refer to atoms, molecules, or ions. In this case, of course, it's the ions we're after. So step number 1, finding the number of moles of calcium nitrate. We are going to use the following formula: molarity multiplied by volume over 1000. We already have the molarity, which is 2, volume is 500 cubic centimeters, over 1000 gives us 1 mole. Our next step is determining the number of ions. Now we're going to do so by looking at the chemical formula of calcium nitrate. Now calcium nitrate will dissolve in water and dissociate to form ions. We are going to have calcium ions and nitrate ions. How many calcium ions? 1. How many nitrate ions? 2 ions, a total of 3 ions. So if 1 mole will give us 6.02 times 10 power 23 ions, what about 3 moles? So we are going to cross multiply, and this will give us our final answer of 1.806 times 10 power 24 ions. So this is the total number of ions that is present in dissolved calcium nitrate. Part B. The electrical conductivity of 2 molar calcium nitrate is higher than that of 2 molar potassium nitrate. Explain. Now, if you look at these two salts, calcium nitrate and potassium nitrate, number 1, both of these are nitrates, and number 2, they have the same molarity. So the only distinguishing factor are the ions, the metal ions. So we have calcium ions and potassium ions. Now, I want you to look at the chemical formulae of these two salts. You'll note that when it comes to potassium nitrate, we have only 2 ions, 1 potassium ion and 1 nitrate ion. But when it comes to calcium ions, we're going to have 1 calcium ion, but 2 nitrate ions, a total of 3 ions. And the reason for this is because of the +2 charge of the calcium ions. So you'll end up having more ions in calcium nitrate dissolved than in potassium nitrate. And therefore, you're going to have better conductivity. Remember, when it comes to ionic substances, it's actually the ions, the mobile ions, that conduct electricity. So the more ions that are present, the better the conductivity. Question number 15. Carbon 4 oxide and methane are gases found in the atmosphere. A. State one disadvantage of carbon 4 oxide in the atmosphere. It causes global warming. B. Name one source of emissions of methane into the atmosphere. Production of natural gas from crude oil, cracking of long-chain alkanes. C. State how emissions of carbon 4 oxide into the atmosphere can be reduced. Reduction of fossil fuel usage, planting of trees. Of course, trees will absorb carbon 4 oxide to utilize for photosynthesis, so less carbon 4 oxide in the atmosphere. Question 16. 5.7 grams of a chloride of element D was found to contain 4.55 grams of chlorine. Part A. Determine the empirical formula of the chloride. Okay, so we are going to determine the empirical formula. Fine. Now, our first step is this. We need to find the mass of element D. Now, over here, we have the overall mass of the chloride plus the mass of chlorine. So, an easy way to determine the mass of element D is simply to take the overall mass by that of the chloride. Now, the difference between the two will give us the mass of element D, 1.15 grams. Now, we can now start. So we have the masses of D and the masses of chlorine. Our next step is inputting the relevant RAMs. So the relative atomic mass of D as provided is 27. That of chlorine is 35.5. Next step, finding the number of moles present in D and chlorine. Now, to find the number of moles, we are going to use the formula mass over RAM. So our mass of D is 1.15, the RAM is 27. The number of moles will be 0.0426. Chlorine, same thing. Mass over the RAM gives us 0.1282 moles. Last step, finding the mole ratio. Now for the mole ratio, we are going to look at the number of moles of D and chlorine, determine which is the smaller value. Now the smaller value, of course, is 0.0426. So we're going to take 0.0426, divide it by the number of moles in both cases, in D and Cl. So that gives us a mole ratio of 1:3. And therefore the empirical formula is DCl3. Part B, given that the relative formula mass of the chloride is 267, determine its molecular formula. So we have already determined the empirical formula. Now we are moving on to the molecular formula. Now the empirical formula is the simplest formula that shows you the whole number ratio of the atoms that are present. So in short, the empirical formula tells you the type of atoms that are present and the simplest ratio in which the atoms combine with one another to form the compound. Now in some cases you find that the simplest formula is also actually the real formula of the compound. So empirical formula becomes similar to the molecular formula. In other cases, you find that the molecular formula is actually different. So the empirical formula is like the simplified version of the molecular formula, which is the case in this instance. So we are told that we need to find the molecular formula. Now we are going to do so by using the following formula. Empirical formula brackets N. Okay, N refers to the number of atoms that we are yet to find out, equals to the RFM, which is 267. So our empirical formula is DCl3 brackets N equals 267. Now we are going to input the relative atomic masses of D and Cl. Now as provided before, RAM of D is 27, and since it's only one, that's it. But when it comes to chlorine, the relative atomic mass of chlorine is 35.5. How many atoms are there of chlorine? 3. So we are going to take 35.5 multiplied by 3, add it to 27. This will give us a total of 133.5 N equals to 267. So what we're going to do is we're simply going to divide. This gives us 2 as our value of N. Now coming back to the initial formula we used, DCl3 brackets N. So N, as we've already found out, is 2. So we are going to open the bracket multiplied by 2, giving us the molecular formula of D2Cl6. Question 17. Table 2 shows the boiling point of ethane, butane, and ethanol. So we have the 3 compounds with their RMMs and boiling points. So let us look at the first one, that is ethane, C2H6. So it has the relative molecular mass of 30 and a boiling point of negative 88.6. The next one is butane, C4H10, relative molecular mass of 58. The boiling point increases to negative 0.5. So between ethane and butane, butane has a higher boiling point and of course a higher RMM. Now the last one is ethanol. The first two belong to the same homologous series, and that is alkane, while the last one, ethanol, is an alkanol. Now let's go to the questions. Give reasons for the following. Part A, boiling point of butane is higher than that of ethane. Now we have butane and ethane, and as stated before, these belong to the same homologous series, alkanes. So they are going to have the same type of bonds. But as from the boiling point, butane has a higher boiling point than ethane. So that means it has stronger bonds compared to ethane. So what could be the reason for this? The reason is tied to the molecular mass. Now, if we look at the molecular mass of ethane, it's lower than that of butane. So the reason for this is because ethane has fewer carbon atoms and therefore it has a lower molecular mass compared to butane. Now guys, what do we mean by a molecular mass? Let's look at the first one, ethane. Ethane has the formula of C2H6. So if we want to calculate the molecular mass of ethane, all we need to do is just sum up the relevant atomic masses. So carbon has RAM of 12. How many carbon atoms are there? 2. That gives us 24. Hydrogen has the RAM of 1. How many atoms of hydrogen are there? 6. So 24 plus 6 gives us 30. Now with butane, you'll notice that the number of carbon atoms has increased. This also increases the number of hydrogen atoms such that at the end you end up having a larger molecular mass than that of ethane. Now in the case of alkanes, an increase in the number of carbon atom increases the strength of the intermolecular forces of attractions. So you're going to end up having stronger bonds in butane than in ethane. Therefore, more energy is required and thus a higher boiling point. Part B, boiling point of ethanol is higher than that of butane. So we are talking about differences between boiling points of alkanes and alkanols. Remember, ethanol is an alkanol, so two totally different compounds. Now, the bonds that are going to be present between these two are going to be different. Ethanol has hydrogen bonds, while butane has van der Waals forces. Now, as we know, van der Waals forces tend to be very weak. So because they're weak, you're going to end up having a lower boiling point. Question 18. Small pieces of beryllium, magnesium, and calcium metals were placed in test tubes containing cold distilled water mixed with phenolphthalein indicator as shown in figure 5. So in this case, we are having group 2 metals, that is alkaline earth metals, reacting with water. By the way, I have a video showing a wide range of metals reacting with water. Actually, it takes you through the sequence of events that occurs when different metals react with water. So if you haven't checked it, be sure to do so. Now in this question, we are being told to state and then explain the observations that were made in each of the following test tubes. So number 1, we are going to be talking about how reactive these metals are in terms of the reaction with water, and then what will happen with the addition of phenolphthalein. Remember, phenolphthalein is an indicator. It's colorless when it's in neutral or acidic solutions, but it changes to pink when in basic solution. Now in the first test tube, beryllium will not react with water. In fact, beryllium is the only alkaline earth metal that does not react with water. The reason for this is because it has a very high ionization energy. So we are not going to have any reaction. The solution remains colorless. Now moving on to test tube 2, we are going to see bubbles, effervescence, because there's going to be hydrogen gas being produced, and we're also going to see a pink color formed after some time. Now the reason for this is because magnesium will react with water to form magnesium hydroxide, which is a basic solution. Now the reaction is going to be a bit slow because magnesium reacts slowly with water. Test tube 3, we are going to have bubbles, effervescence, and the solution will also turn pink. The reaction will also be faster compared to that of magnesium. Question 19. A laboratory assistant wanted to investigate the effect of an electric current on substances. Figure 6 shows arrangement of the apparatus used. Now, if you look at the arrangement, we have apparatus A, B, and C. In A, we have hexane, B, mercury, and C, we have aqueous sulfuric acid. So these are supposed to act as our electrolyte. Now, in this case, we are going to observe, or we want to find out whether electrolysis will take place. Electrolysis is a chemical process whereby an electric current is passed through a substance, and then the substance undergoes chemical decomposition. It breaks down. So let's discuss this first. Let's start with setup C. In setup C, we have aqueous sulfuric acid. Now, aqueous sulfuric acid will dissolve in water and then dissociate to form 2 ions, hydrogen ions and sulfate ions. Now, due to the presence of the mobile ions, this will be able to conduct electricity, so it can act as an electrolyte. Part B, we have mercury. Mercury is a metal. Metal contain delocalized electrons. So yes, it can also conduct an electric current. Will it be able to carry out electrolysis? Of course not. When you talk about electrolysis, we are talking about, yes, a substance, number 1, conducting an electric current, and then number 2, undergoing chemical decomposition, breaking down. Now, mercury can do the first. It can conduct an electric current because it contains delocalized electrons. But it cannot undergo decomposition because essentially mercury is just an element. What will it break down to? Now, when it comes to A, hexane cannot act as an electrolyte. It is not a conductor of electricity. And the reason for this is because this is molecular. It does not have any ions, nor does it have any delocalized electrons. So we should not expect any electrolysis to take place in A. So explain why. In A, the bulb did not light up and no electrolysis took place. So hexane is not an electrolyte because it is molecular. So it cannot conduct electricity. Now part B. In B, the bulb lit but no electrolysis took place. So as stated, the reason why the bulb lit up will be because an electric current is being conducted, and the reason for this is mercury is a metal, so it contains delocalized electrons. Electrolysis cannot take place because mercury is an element. Part C. In C, the bulb lit and electrolysis took place. So aqueous sulfuric acid is an electrolyte. So it contains ions, mobile ions, that number 1 can conduct an electric current, and number 2, they can be discharged. You know, they can gain electrons or lose electrons. So electrolysis will definitely take place. Moving on to question 20. Carbon-14 is a radioactive isotope of carbon. It decays to form an isotope of nitrogen. Part A. Write a nuclear equation for the decay process. Let's start with the term isotope. So what is an isotope? Now, isotopes are atoms of the same element. These atoms have the same atomic number but different mass numbers. Okay, let's break that down. So we're talking about atoms of the same element, okay, whether carbon, nitrogen, oxygen as such. Now these atoms will have the same atomic number, will have the same number of protons but different numbers of neutrons. Now because they have the same number of protons, they are from the same element. Remember, it's actually the protons that determine which element this will be. So for example, if you have an atom that has 6 protons, that automatically makes it carbon. So for example, in the case of carbon, carbon has 2 isotopes. We have carbon 12 and carbon 14. Now in the case of carbon 12, you have 6 protons and 6 neutrons. So a total of 12. So the mass number is going to be 12. In the case of carbon 14, we have 6 protons again, but the number of neutrons is 8. So what is the mass number? 14. So as you can see with these 2 isotopes, the atomic number is the same, but the mass number is different due to the different numbers of neutrons. Now, when you talk about radioactive isotopes, these are simply isotopes that can undergo radioactivity. You know, they can break down to form a smaller nuclide. So let's start with our nuclear equation. So we are going to have our isotope, carbon, that has an atomic number of 6 and a mass number of 14. Now we are told that this will undergo decay. It will break down, leading to the formation of an isotope of nitrogen. Now an arrow and then nitrogen. Now what is the atomic number of nitrogen? It's 7, of course. Mass number will be 14. Now I want us to compare. Look at the mass numbers. There's really no change. It's still the same, but the atomic number has changed. It has increased by 1 from 6 to 7. So which type of radiation is this? That's right, it's beta radiation. So when it comes to radiations, we have 3 types. We have alpha, beta, and gamma. Now each has a distinctive arrangement, let's say. Now when it comes to the beta radiation, that is how it's illustrated. Now with the beta radiation, how is it formed? You have a neutron that is present within the nucleus converting to a proton and an electron. Listen to that. So a neutron changes itself to a proton and an electron. Now, of course, the proton will remain within the nucleus, but the electron will then be ejected. And this is how it's illustrated because it has a negative charge. Now, what about the change in the atomic number? Now, coming back to the mass numbers, actually, let's start with the mass number. The mass number does not change. The reason why it does not change is because when we talk about the mass number, it's the sum of the proton and neutron. So if you sum up the number of protons and the number of neutrons, you get the mass number. When it comes to this type of radiation, we are talking about a neutron changing to a proton. So at the end of it, yes, you're going to have 1 less neutron, but if you sum them up, you're still going to end up having the same number because you're decreasing the neutron, but you're increasing the proton, and ukizi add, same thing. Now, atomic number, of course, will change because atomic number refers to the specific number of protons. So we are increasing the number of proton by 1. So this is why it changes to 7. And there we have it. Part B. Archaeologists calculate the age of organic matter using the proportion of carbon-14 present and the half-life of carbon-14. Roman 1. State what is meant by the term half-life of carbon-14. Now, half-life refers to the time taken for a radioactive isotope to decay or to break down to half of its original mass. Roman 2. Given that the half-life of carbon-14 is 5570 years, calculate the age of a piece of bone found to contain 1/16 as much as carbon-14 as living matter. So essentially, we are being told that it takes 5,570 years for, let's say, 1 gram of carbon to break down to a half a gram. So if we are to assume that the carbon has decayed to 1/16, how many years has it taken to do so? So we are going to start with 1. This is going to be our initial one. So it's going to take 5570 years for it to decay to a half. And then from a half to a quarter, another 5570 years. And then a quarter to 1/8, 5570 years. We are just breaking it down by half. So a quarter, the half of a quarter is 1/8. 1/8, we are moving to 1/16. And that is our last one. So we are going to sum up all of these years to give us the total amount of years it takes for the mass of carbon to decay by 1/16. So how many half-lives do we have there? 1, 2, 3, 4. 4 half-lives. So if one half-life is equivalent to 5570 years, 4 will be equivalent to 22,280 years. A student used the following procedure when standardizing sodium hydroxide. The student placed 25 cubic centimeters of the hydroxide in a conical flask and titrated it using 0.1 molar hydrochloric acid and phenolphthalein indicator. The average titer was 21.5 cubic centimeters of the acid. State and explain how each of the following steps in the procedure may have affected the titer value. Part A. The student rinsed the conical flask with the sodium hydroxide before using it. Now rinsing will leave a little bit extra sodium hydroxide in the flask, which will overall increase the titer value. Part B. The student did not rinse the freshly cleaned burette with the hydrochloric acid before filling it. So when you're using your burette, number one, you're supposed to clean it thoroughly with water, of course, and then you're supposed to rinse it a bit with the solution you're supposed to add. So what this student did was, he did not rinse with hydrochloric acid before using it. So some water was left in the burette after cleaning. This diluted the hydrochloric acid, increasing the titer value. Part C. The student used about 2 cubic centimeter of phenolphthalein indicator. Now phenolphthalein is a weak acid. This reacts with a little bit of the sodium hydroxide, and this lowered the titer value. Question 22. The setup shown in figure 7a was used to determine the approximate percentages of the major components of air. So we have phosphorus, and we should assume that the phosphorus is supposed to react with the active part of air, and that is oxygen. So part A, complete figure 7b to show the setup after it was left standing until no further changes were observed. So that is how the setup is supposed to look like. Now the reason why it's supposed to be drawn as such is because number one, phosphorus will react with the active part of air, and that is oxygen. Now this will create a partial vacuum in the jar. Now atmospheric pressure will act on the water, causing it to move into the jar. So we should illustrate in our diagram that the volume of water increases within the gas jar and reduces within the water trough. Part B, explain how the percentages of the major components of air are calculated. So we are going to divide air, or we are going to group it into two. The active part of air, which of course is going to be oxygen, and the inactive component consisting of the remaining gases. Now, if we want to calculate the percentage of air, of oxygen that was used up, we need to have the final and initial heights of air. Now, the initial height we are going to label as HI, H initial. Now, this is what was present at the beginning of the experiment. The final one is what was left at the end. So this becomes our HF. So we are going to use the formula, percentage of air by volume used up, height of air used over the initial height of air multiplied by 100. Now, the height of air used can be given by HI, which is the initial minus the final. And then of course over the initial multiplied by 100. So that is it. Now if we want to calculate the percentage of the inactive component, this is the component that was there at the beginning and at the end. It remained unchanged. We can simply go to HF, which is the inactive part, over the initial HI multiplied by 100. Question 23. The heat energy value of a fuel is defined as the amount of energy produced by 1 gram of the fuel. Calculate the heat energy value of the fuels, hydrogen and ethanol, and complete the following table. So we have hydrogen and ethanol, their molar enthalpy of combustion, and the heat energy values that we're supposed to fill in. Now let's define what is the molar enthalpy of combustion. I know that it's written as enthalpy of combustion, but if you look within the brackets, the units are kilojoules per mole. So this simply means that if you were to take 1 mole of hydrogen gas, combust it or burn it in air, it's going to release 286 kilojoules of heat energy. Same goes for ethanol. If you were to combust 1 mole of ethanol, it's going to release 1371 kilojoules of heat energy. Now we have been told to calculate the heat energy. Now you can simply calculate heat energy by using the following formula. You can take the molar enthalpy of combustion, divide it by the relative formula mass of the fuel. So we have the molar enthalpy of combustion. We've already been given that. For hydrogen, it's 286. For ethanol, it's 1371. Relative formula mass is also easy to obtain. So for hydrogen, the relative atomic mass is 1. How many hydrogen atoms do we have? 2. So we take 286 divided by 2, giving us a heat energy value of 143. Now ethanol, we need to find out the RFM. So we are going to take carbon. Carbon has the RAM of 12 multiplied by 2. Hydrogen, how many atoms do we have? We have 6, 5 and 1. So atomic mass is just 1. So 24 plus 6 plus oxygen 16. This gives us the relative formula mass of 46. 1371 divided by 46 gives us 29.804. Part B. Other than its heat energy value, state one advantage of using hydrogen and ethanol as fuels. Now, the advantage of using hydrogen is that it does not pollute the environment because the product that is formed is water. Roman 2 ethanol. Ethanol is a renewable source of energy. Plus, it's easy to store and easy to transport. Next question. Study the structures of substances L and M shown in figure 8 and complete table 4 by giving the names that describe the type of structure and bonding in each substance. Now, if you look at substance L, that is a structure that you'll typically find in ionic substances such as sodium chloride. So, the structure is a giant ionic structure. The bonding, of course, ionic, which is also known as electrovalent bonding. Structure M. Now, M is a giant atomic structure that is found in compounds that have covalent bonding. 25. State one physical property that will suggest the presence of each of the following gases from a leaking gas cylinder. A. Hydrogen sulfide. This is the characteristic smell of rotten eggs. B. Nitrogen 1 oxide, a sweet odor or a pleasant smell. And lastly, chlorine gas. You're going to have a gas that is yellow-green in color. 26. Part A. Give the names of the types of compounds whose reaction is described as esterification. So in short, the question is asking us which compounds are involved in this process. So we have two, alkanoic acids and alkanols. These two react with one another to form a compound called an ester, and the process is known as esterification. Roman 2. Saponification. Now, saponification is a process that is used for the manufacture of soaps. Now, if you want to create soaps, you need to have a fat or an oil and an alkali. Suitable ones are potassium hydroxide or sodium hydroxide. Part B. State the importance of vulcanization. Now, vulcanization is a process whereby, or it's a process that is employed to harden rubber. Now, synthetic rubber tends to be soft, which is not ideal. So it's heated with sulfur in order to make it tougher and stronger. This improves the quality of the rubber. Now, this process is what is termed as vulcanization. So the goal, of course, is to make the rubber stronger and tougher and less flexible. Our last question. Figure 9 shows a setup used to separate a mixture of two liquids, Q and R. So we're supposed to identify 3 mistakes that are in the setup and give a reason for each case. Now, mistake number 1 has to do with the thermometer. The thermometer has been dipped in too far inside the fractionating column. Now, it should be at the end of the adapter as such. Remember, the function of the thermometer is to measure the temperature of the vapor. Mistake number 2 is the use of a water bath. Why are we even using a water bath in this case? If you look at the two liquids that we have, Q and R, they both have boiling points that are higher than water. So it doesn't make sense to even use a water bath. And our third mistake is with the condenser. Now you'll find that the outlets for water in and water out have been reversed. And this, of course, will cause condensation to not be effective. And that brings us to the end of this lesson. Be sure to check out my next video where I'll be discussing paper 2 of chemistry.